So, welcome student to the next class of Introduction to Nonlinear Optics and its application. So, in the previous class we have started a very important concept regarding phase matching. This is called quasi phase matching, and the basic principle of the quasi phase matching was to find out a suitable phase through D, which is a nonlinear coefficient. Now, D will be varying sinusoidally, so that it can compensate the additional phase that is happening due to the phase mismatch delta k. So, delta k is compensated by another quantity we call k q, which is coming because of the fact that my D matrix or the D elements is now periodic in nature. So, that basically give rise to another quantity which is some sort of wave vector we call k q, that will now going to compensate the delta k, and that is why we will get a phase matching, a different kind of phase matching. The interesting fact of this kind of phase matching is that we do not require any kind of birefringent crystal for that, any kind of material we can use, and today we will going to find out how we can eventually make this D value varies periodically, which is not very easy job to do, but we can make a system where D can vary periodically, but not with a sinusoidal function, rather a step function. So, if a step function is there, then how to handle that thing and how the our calculation is modifying, that we will going to do in this course. So, let us see what we have in this course. So, quasi phase matching, which is the thing that we have already started, and then periodic D function, as we already mentioned, that if the D function is periodic, what kind of thing, what is the consequence we have, that we are going to learn in today's class. So, let us see this structure. So, in quasi phase matching, the important thing is that this phase k q is now related to another quantity delta k, or delta k is related to another quantity k q. This is the old figure. Because of this phase match, we have the improvement in this eta value. Eta is a some sort of quantity which can give you what is the percentage of energy that is transformed from fundamental to second harmonic. So, this is something called efficiency. So, how the efficiency is going to improve by introduction of this quasi phase matching thing is shown in this figure. When delta k not equal to 0, that is the most general case, we find that efficiency is there, but also it is going down. If delta k equal to 0, that is the most ideal case, we find efficiency is going as a function of z square, that we also learned in the previous class. But delta k equal to kq is some sort of intermediate process, where we can improve the efficiency, but not the way we have here delta k equal to 0. However, delta k equal to 0 is the most unrealistic condition, because we find that delta k equal to 0, in this condition the efficiency will vary as a function of z square, when we consider a very important approximation that my pump, that means the fundamental field is constant, but in real case this is not true. So, we will not going to get this kind of efficiency, or the efficiency may not be a function of z square. So, we will find that in the later class how the realistic calculation gives the efficiency, but today we will going to learn about quasi phase matching. So, this kind of phase matching or this kind of efficiency we will get when we have a phase matching condition under quasi phase matching case. So, this is the figure in the left hand side, where we can see that this plus minus sign basically designate the nonlinearity of the system. So, here the nonlinearity D value is plus, here it is minus, here again it is plus, here it is minus, and so on. and we have a period here. So, this is the period. In one period we have the we have the variable d, which is plus to minus. So, once we have this kind of structure, this minus d basically give rise to additional phase, and this basically compensate delta k. That is the idea. So, today we will going to do more detailed calculation. So, in order to find out this periodicity of d, because d, if you remember, d, this is a function of dz, and it was d0 sine of kq z. This was the form of d. This kq basically corresponds to the phase, and this kq corresponds to the period, and this kq is equal to 2 pi by lambda. This lambda is basically the periodicity of the system. So, here we can see that in one period the d value will go maxima and then go minima and then again go to 0, and that is the standard sine curve. On the other hand, if I compare this periodicity with the periodicity that we have in finding the efficiency in delta k not equal to 0 case, that we have shown in the previous slide, that it will vary like this. So, there is also a periodicity, and we know that LC is a length which is called the coherence length, at which we have maxima here. So, here we find that when we have a maxima and then after that this is going down, what happened in this case, we will compensate this phase with this additional phase incurred by this d value. So, this is the concept, and using this concept we can find out what is this lambda. Now, one can also find out the lambda. So, if I consider this is a phase matching, so kq is equal to delta k and 2 pi by lambda, LC is equal to lambda by 2. Very easily we can see that the LC should be the half of the period whatever we have in periodic d, and delta k, which is k 2 omega minus 2 k, or k 2 minus 2 k 1. So, now if I use this expression together, then we can find that delta is this value. So, if I know the refractive index at 2 omega, if I know the refractive index at omega, then readily we can find out what should be my periodicity. So, this we have already done in the previous class. So, this is some sort of review of the previous class. So, today we will going to learn more important thing, that we mentioned in the previous case that d is varying sinusoidally, which is the most ideal case, but in fact it is not possible when we try to do in realistic case. So, in realistic case what happened? So, we have a periodic nonlinearity. So, that means the value of d here, so the value of d from here to here not going to vary. So, it will be a constant value. For sinusoidal case, if I plot here, for example, for sinusoidal case it will be something like, the variation will be something like this. This is roughly the sinusoidal variation. But the sinusoidal variation can be approximated by these step like functions, because we know that from here to here, which is from this point to this point, what happened, the d value will remain constant. So, there will be no change in d value as shown here. In sinusoidal case the d value is changing, but if I put some crystal here, the d value remain constant from here to here. Now, what happened after this point, we will put the crystal in such a way that the value of d is negative. So, suddenly we have a drop. So, d value will go to negative side. So, if this point is plus d0, this point will be minus d0. So, it will vary like this, it will not going to vary sinusoidally. So, we need to take care of this issue, because when we developed the theory in the previous class, we consider d as a function of z as d0 sine of kq of z. This was our assumption that D is varying sinusoidally, but in real case we find that it is not varying sinusoidally, it is varying, but it is varying in a step like function from positive to negative. So, we will handle this issue today, but before that we need to know how we make crystal positive D to negative D. That is important, because I am using the same crystal and I put these two part of the crystal in such a way that in one portion of the crystal I have a positive D value and in another portion of the crystal we have negative D value. So, how one can make this we need to find out. So, the process is not that difficult, to be very honest. So, we can just one treatment is, if we just rotate the crystal or change some kind, put some kind of operation of the crystal, so that the D component become minus D, then the thing can be done very easily. For example, here suppose we have a crystal, this crystal has two part, this is part 1 and this is part 2. This is a laboratory frame and we know that for any crystal we can write our D matrix for a given coordinate system. So, normally the D matrix is written in terms of principal axis. So, big X, big Y, big Z, capital X, capital Y, capital Z is a coordinate system which basically gives us the principal axis. So, this is under principal axis is big X, big Y, big Z or capital X, capital Y, capital Z. In part 1 what happened, this coordinate system is suppose coincide with the lab frame. So, we have a D matrix here for this particular system or this particular orientation. Now, what we will do in part 2, we will make a rotation of say theta equal to pi. That means, this Z will go down, and since this is a right handed coordinate system, it is a left handed coordinate system. So, x Z goes to here, y goes to this point and x remains same, because I am making a rotation around x point. So, now my principal axis is changed compared to my lab frame axis. So, whatever the D value we have under this rotated coordinate system should be different from the previous one. So, let us take one example, then these things may be clear. So, we will going to do the same thing for lithium niobate crystal. We know that for lithium niobate crystal the quantity D33 is maximum, it is of the order of 30 picometer per volt. In the last class I think we discussed this issue. Now, what happened that we will going to make a pi by pi rotation around x axis. So, this is our principal axis. For this principal axis the D matrix is written here, and now for example, to have the quasi phase matching, the D33 is a quantity that we are going to use. So, there are many D components here, but D33 which has a maximum value, we will going to use these 33 to achieve quasi phase matching. So, that means our aim should be, if I rotate this system to theta equal to pi around x axis, then what should be the value of D under this rotated system. So, we know the what is the form when the matrix or a tensor is rotated to certain angle or make some kind of transformation. So, if I put some kind of transformation over that, then what happened, that the coefficient is going to change, and we know the coefficient can be written in this general form. So, d I j k prime is the coefficient of I j k of D matrix at prime frame, and it is related to the coefficient of non prime frame d alpha beta gamma, and r alpha I, r beta j and r gamma k is the component of the matrix that basically leads to this kind of transformation. So, in this case it is rotation. So, we know that for rotation matrix what is r, and now if I put say theta equal to pi, that means I am rotating pi along x axis. So, my R matrix will be having this particular form. So, I know what is my R 11, R 12, R 13 and so on. So, now if I try to put this rotation, try to find out what happened the D33 component under this rotation, then we are going to use this, and when we are going to use this expression for D33, I need to put D33 prime, because I need to know what is the new form or what is the value of D33 in prime frame. So, once I put D33, I need to put ijk is equal to 3, 3 and 3, then I put alpha 3, beta 3 and gamma 3, and alpha, beta, gamma should be sum over. So, then alpha, beta, gamma should take 1, 2, 3 value for all the cases. But we find that R matrix is such a way that only the diagonal elements are there, all the other elements will 0. So, when I write R alpha 3, the alpha has to be 3, because only R33 coefficient is non-zero, that is this one, all the other elements is 0. In the similar way, R beta 3 also can be represented as R33, because other elements are 0, and R gamma 3 also represented by R33, because other elements is 0. So, since the other elements are 0, then R33, 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 we put the value of R33, which is minus 1, minus 1, minus 1. If I put 3 minus 1, then we find that D33 prime is related to D33 with a negative sign. That means, in the rotated system, or if I rotate the crystal and then if I try to find out what should be my D value, then we find that the D value, at least the component 33 component, is now a negative value of the previous one. That means, before rotation, whatever the D value we have, after the rotation in rotated coordinate system, this value is changed and this value is a negative of whatever the value we have. So, that means, if I just change or rotate the crystal and coupled it with the previous crystal, then we have a structure like that, where in this part we have D plus, say D33 which is plus, and this part we have D33 minus. And if I do the same thing with by putting all these things together, then we will have a structure where we have a variable D. So, one portion it is D positive, another portion D negative, one portion positive, negative and so on. Okay, so, now since we have, as I mentioned, the D function is not sinusoidal, it is a periodic function, but it is a some sort of block kind of function. So, we need to take care of this issue, and we need to find out the Fourier components of this, so that we can find out what is the corresponding Fourier component that we are going to use. So, let us try to understand this D function first. So, here we plot the D as a function of z. So, this is the period from this point to this point, suppose we have the period. So, this period is lambda. You can see that this particular structure will be there for right hand side and left hand side. So, this is a repetitive structure. So, this structure, that is why from here to here, this point to this point, we write it as my period lambda. From here to here, we say this length is L. So, the ratio lambda and L is called the duty cycle. So, that we are going to use in the later, but we should know. So, the function is something which is shown here. D is equal to D0 when delta of z is less than L by 2. So, this point is L by 2, this point is L by 2. So, when the delta z, that means from here to here the value of D is positive. When delta z is mod of z is less than delta 2, greater than delta 2, but less than big lambda by 2. So, we are basically considering from here to here this point and here to here this point. At this point in this region, this basically this point is lambda by 2, this coordinate is lambda by 2, this coordinate is minus lambda by 2, this point. So, minus lambda by 2, 2 minus L by 2, the value of d will be minus d. L by 2, 2 lambda by 2, the value is also minus d. So, this minus d obviously in this range. This is the range where the d value is minus d. So, we define the d value or we define the d function, and based on this function we can try to find out what should be the functional form. So, now one thing one should note that d has a periodicity lambda. So, d function should be written in such a way that dz by lambda should be equal to dz. This is the form of a periodic function, we know that. So, suppose we write d as this is basically a Fourier form where these are the Fourier coefficients. So, I am making a sum over this quantity to represent a periodic function. We can always represent a periodic function in this way. So, if the function is periodic, we represent this where Gm is a Fourier components of that. Now, if I write dz plus lambda, then it should be Zm e to the power I k. In place of z, I write z plus lambda. So, in the next step, it should be Zm e to the power I m k z into e to the power I k m k z, this quantity, k e to the power I m k q lambda. K q lambda, we know it is how much? It is 2 pi, because k q was lambda divided by 2 pi divided by lambda. So, k q into lambda is equal to 2 pi. So, once we have these things, then this thing we can replaced by e to the power of I 2 pi into m, where m is an integer. So, this quantity is eventually 1. So, if I go back to the next slide, then we can see that since k is 2 pi by lambda, dz plus lambda is equal to this quantity, and when I put this, this is something which is valid. So, that is why the point is d can be represented in that summation form. So, next thing that is important is how to find out this Gm, because Gm is something which is important. So, d can be dz can be represented for this periodic function. This is the realistic function of d. So, we can write d as summation of m tends to infinity, m from minus infinity to infinity. So, Fourier as a Fourier series. So, Gm is a Fourier component. So, Fourier component can be represented if the function is given. We know that if this is given, then Gm can be represented over the full period, then the given function and e to the power I minus m kz dz. So, if the functional form is given, and then if I integrate to over the period with 1 by period, then we will have the value of Gm. So, now the function is given. So, fz is given to us, which is already shown in the previous slide, that d is equal to d0 and equal to minus d0 with mod of z is less than L by 2 minus L by 2 L by 2 this region. And okay, so let me go back to previous slide. Then the d function, definition of the d function is there. So, it is less than L by 2 and greater than L by 2. When I put the mod sign, I do not need to put the other limit. So, this is the definition of G, definition of d function. So, now what we will do here, we will find out what is my Gm. So, Gm is defined by this. So, we will integrate part by part. So, first we integrate from this point to this point, which is minus lambda by 2 to L by 2. So, when minus lambda by 2 L by 2, we integrate, the value here is minus 1, because I have already put d 0 outside. So, function here is basically minus 1. So, we put function minus 1 e to the power I m k z. Okay. Then the next part is from, I integrate from here to here first, then I integrate in this region here to here. So, this point it is L by 2 minus, and this point it is L by 2 plus. So, minus L by 2 to plus L by 2 I integrate, and here the value of d is plus 1. So, this is plus 1 e to the power minus I m k z, z will be there. And finally, we have 1 by lambda from here to here, the length is, the limit is here plus L by 2 to plus lambda by 2. So, minus 1 e to the power I m k z z. So, we can divide the total integration into 3 parts. The first part I can say this is I 1, and second part I say it is I 2, and third part the integration is I 3. So, now the next thing we need to evaluate the I 1, I 2, I 3 independently, and then I find what is my GM. So, first I 2 part, which is easier, because I am making a limit minus L by 2 to plus L by 2. So, the function is plus 1 here, it is the power I. So, I just readily integrate. So, when I integrate, it will be e to the power I m k z z divided by I m k z, with the limit z equal to minus L by 2 to plus L by 2. Now, if I put these things here, then what we will find, e to the power, here we can find e to the power minus of I m k z L by 2 minus e to the power of I m k q L by 2. So, first we will find e to the power I m k q L by 2, and then we will find e to the power plus I m k q L by 2 divided by I m k q. So, if I take this common and if I consider this, it is nothing but minus of 2 I sine of m k q L by 2, which is shown here. This is the quantity we will have. So, from here we can easily find that this is sine, and now if I put the value of k q, then k q is 2 pi by lambda. So, 2 pi by lambda if I put here, then readily we can find that this value is nothing but 1 by m pi sine of m pi L by lambda. Now, I can also use this quantity, which is a duty cycle, very important quantity. So, this become I 2 become 1 by 2 pi, and if I put this ratio L by lambda to d, so m pi by d. But what about I 1 and I 3? So, I 1 also exactly in the similar way, if I do, then we will find it is e to the power I k m k q L and pi L by this quantity. I 3 also we can do in the similar way, and we will have a similar kind of quantity. When we add these two, mind it, the limit is different here. Here the limit was minus L by 2 to plus L by 2, that is why we can readily have the sine form, but here it is minus lambda by 2 to plus lambda by 2. So, that is why the limit is different, and since the limit is different, we will not going to get the sine term directly. So, what we will get, if I now add these two things, then one term here and one term here, one term here and another term here can be, from these two can be considered, and when these two term we consider, we will find two term like sine and sine. One is for one the argument is m k q L divided by 2, in other case the argument is m k q lambda by 2. So, these two when we add, then we find that k q lambda by 2 basically gives me sine of m pi, which is 0, because sine of, we know that sine of m pi, where m is an integer, this quantity is 0. So, eventually we will come that I 1 plus I 2 is 1 by m pi sine of m pi L by lambda. Now, L by lambda is d. So, we will have 1 by m pi sine of m pi d. If you look here, we have already got the same thing for I 2. So, I1 plus I2 plus I3 is eventually 2 divided by m pi sine of m pi into d. So, this is the important quantity, because in the future classes we are going to use, we need to find out what is the value of g. Gm is a general term. If I want to find what is Z0, then if I put 0 here, you will find at the limit g tends to 0, this limit goes to 1 or some value, because I need to put a d multiplier. So, it should be around this value should be 2 divided by d or something, or if this value is around 2. So, in the similar way we can find what is my G1, G2, G3 and so on, that this kind of value we will going to use in the next class. So, important thing is you need to make sure that you know what is the value of g when the function of function of d is periodically changing. When the function is periodically changing, the value of g, the Fourier components, can be calculated, and it should be like this. So, with this note, let me conclude today's class. So, today we learned mainly how the quasi phase matching terms are there. If the periodicity of d is there, it is not sinusoidal. If it is a block kind of function, then how to handle these kind of things? We need to find out the corresponding Fourier components, and we find the corresponding Fourier components in terms of Gm, which we will going to use in the next class. So, today we will like to conclude here. So, let me finish the class here. So, see you in the next class, and thank you for your attention.